Come back. Let's continue discussing gravity as a Gaussian space with Gregoire Matthys.
Hi everyone. Let me first be the organizer for allowing me to speak here. So today I'm going to tell you about a recent paper that came out with Kurt Interbichler, Diego Hoffman, which used to be my advisor in Amsterdam, and Austin Joyce. And so the main question that we were trying to answer is this one: what defines a theory of linearized gravity? So obviously, we would like to remove the word linearized here, but this is too much to ask to begin with, so we're going to focus on this case for now. And as a disclaimer, every time I use the word gravity during this talk, what I really mean is linearized gravity. And I'll comment on GR and more at the end. So a potential way, or a potential definition, could be to say that this is a theory which is coordinate invariant. But this is not really satisfactory because, well, this is more about the gauge symmetry than about the theory itself. And so this cannot be the true essence of gravity. Another try could be a massless spin 2 in the spectrum, because they're pretty powerful theorem that tell you that if you have a theory of a massless spin 2, this reproduces the interaction of Einstein gravity. This is better because we've gotten rid of gauge symmetry, but we still want to explain the masslessness of this spin 2. So the usual way people say that this thing has to be massless is because you have a gauge symmetry and blah, blah, blah. But this is not really satisfactory either, and we're trying to see whether there is a structure in linearized gravity that protects the masslessness of this spin 2 particle. And so this talk is going to be about trying to see whether we can come up with a structure where the masslessness is built in.
Sorry. I mean, if it's massive, it has more degrees of freedom, so it's already protected in the sense that you have a different number of degrees of freedom if it's massless or massless.
Sure, but I mean, we believe that the graviton has to be massless, right?
I thought you were saying that you need something extra. I think that will already be enough, but maybe you have a different perspective.
Yeah, maybe you can ask at the end if you still have the question. Okay. So a famous source of gapless mode is the Goldstone theorem that tells you that if you have a broken symmetry, then you have a gapless mode. Now you run into trouble because, well, you know that a UV complete theory of gravity cannot have global symmetries, but this is not the case of linearized gravity. And in particular, I will tell you that this theory has global symmetries, and this global symmetries implies a Goldstone theorem, which protects the masslessness of the gravity. The key here is that the symmetries are not regular symmetries, but they are highly formed symmetries. And in particular, they are higher biform symmetries. And I'll explain to you later what this means. But you have a symmetry where you shift the metric perturbation, h mu nu, by a symmetric 2-index object. And this type of symmetries imply a Goldstone theorem which protects the masslessness of the gravity. So this has been a modern trend in condensed matter physics that people use global symmetries and anomalies to constrain the low energy effective field theory of some systems. And a particular example of that is a superfluid. So if you take a superfluid, you can define this. You can define this as a theory which has a regular U1 times the d-2 higher form U1 symmetry, and the two are coupled through a mixed anomaly where sorry, this is the U1 current, so it's a 1 form. This is the D-1 current associated to this D-2 form symmetry. I took a star of this, so this is always a 1 form. And this is the conservation of this current is anomalous, and it picks up the field strength of the regular U1 symmetry. And so this is enough to tell you that this is a superfluid. If I give you this global symmetry structures and those two equations, you're sure that this is a superfluid. The same with Maxwell. So Maxwell, you have F and star F, and an anomaly structure, and this fixes the low energy action to be the one of Maxwell. So our goal today.
Sorry, can you repeat what's K? KU?
Yeah. So right, a 0 form symmetry has a 1 form current. A D-2 form symmetry has a D-1 form current, and K is the D-1 form current associated to this U1 to the D-2 form symmetry. And I took a star because, well, the star is always a 1 form, so it's easier. And like, you know, conservation and dual conservation are related by the star. So
what is a superfluid in this very formal context?
Yeah, it's just d mu phi squared. It's like you take a boson on a circle and you integrate out the radial mode, and this is the EMP you get.
So what is K in that description, in that effective field?
So K.
Can we use a quantitative theory word rather than say a superfluid? What are we doing?
Yeah, I'll come back to you. So K is just this. So this thing is it's what I will call a magnetic symmetry, because it's always conserved thanks to a Bianchi identity, right? And so this symmetry you're not going to break, but you can break the other symmetry if you want. Sorry, what was your question again?
Just asking what is a superfluid. Here, you're writing some equations, and then.
Yeah. So here, what I really mean is just. D mu phi squared plus. So a superfluid is a P of, right, a superfluid is like a P of X theory in general. And X is like the square root of the covariant derivative. And you integrate that out and you look at the low energy effective action, and this is what you get.
So massless here.
Yeah. Yeah, you take a boson living on a circle and you integrate out the radial mode.
Yeah, massless scalar with a shift symmetry. You can think the U1.
Yeah, exactly. You have a shift symmetry. So this U1 is just a shift symmetry of the boson, and this one has this conserved current, which is just topological. Okay. So this is the simplest example, and this is in a paper by Luca Della Creta, Diego, and myself. And so, as I told you, the goal today is to try to see whether we can do something along these lines with linearized gravity. So I don't want to write an action. I will eventually write an action. But the goal is really to try to define the theory with a global symmetry structure and an anomaly structures. And you can do that in E&M. Like you have F star F, a Bianchi identity, a Maxwell equation, and an anomaly, and this defines the low energy E&M action for you. There is no way to escape. So let me do a crash course on higher form symmetries to bring everybody in the loop. So I'll start with a zero form symmetry, or just a regular symmetry. And in this case, you have a point like operator O, which creates excitations. The excitations propagate in space-time, and then if you take so time is going like that. If you take a fixed time surface and you integrate the current, or like the star of the current, this object is conserved because the current J is conserved, or this object is topological because the current is conserved. And this counts the number of such excitations going through the surface. And the main difference that I want to advocate for between higher form and zero form symmetries is that if you were to choose a different surface here and try to commute these two charges, so this is Q1 and you can do Q2 here, and you try to commute Q1 and Q2, then these two surfaces have to touch at some point, and when they touch and something special happens, you get a non-abelian symmetry, and if they touch and nothing special happens, you get a if they touch, nothing happens, you get an abelian. If you touch, something happens, you get a non-abelian symmetry. But there is no way to escape the fact that these two surfaces will have to touch if you try to commute them. And in particular, the current here, J mu, is always a one form. For high form symmetry, the objects that create the excitations, so let me take a p-form symmetry. The object that creates the excitation now, so the O, are p-dimensional extended objects, and the current are p plus 1 form. And if you wanna count excitation, so you have this operator O, which is an extended object. If you wanna compute the charge, you have to wrap this thing with a charge operator. So this is a one form symmetry in 3D. So the codimension is also 1. So the charge operator are also lines. And you see now that the charge operator. So the charge you integrate over d minus 1 minus p surface. And you also integrate the star of this current. And so if now you put a second charge here, the statement is that you always have enough codimensions to make that circle bigger, commute that circle, and then shrink the circle again. And so that's the easy and quick way to see that this higher form symmetries always have to be abelian. There is no way to make a non-abelian higher form symmetry.
Sorry, can I ask one more question about the supercode example? The claim wasn't that if you just have those two symmetries that the low energy theory is this free boson. It's that if you have those two symmetries and one or both or something of them is spontaneously broken, then you have this.
Well, I don't even have to tell you that they're spontaneously broken because I'm in the phase where they're already spontaneously broken. I never have to say the word spontaneous symmetry breaking.
But yeah, why don't you have to say it? Couldn't they, in principle, not be broken, and then the IR theory might be trivially gapped or something? Or?
Well, they could, but then the low energy action will not be of that form.
Right. But then don't you need to say? Yeah, maybe I'm not understanding.
Yes, I mean, I need to say it, but I don't need, like, this defines the theory for me, and this, I can prove Gaussian theorem with that. I never have to tell you there is a symmetry that gets spontaneously broken, the Vev picks up, like the boson picks up a Vev, blah, blah, blah. I never need to say all these things. I can just tell you a symmetry that has a U1 times U1 to the d minus 2 symmetry, and this anomaly has a Gaussian boson. I don't need more information than that. And so this is another proof of Gaussian theorem, which does not require all the usual mumbo-jumbo, and in particular, this applies in d equal 2. Like this structure is just true in d equal 2 as well, and you can show Gaussian theorem in that. So it's like an axial type anomaly, but it exists in any d. Just in d equal 2, those are both trivial U1 symmetries. You don't have to talk about higher form symmetries, but the structure is just there, and you can show that there is a gapless mode in the spectrum.
So when you say that you can prove Goldstone's theorem, you're saying that there is a matrix element between J mu and the vacuum and some state P, or there is some pole somewhere?
Okay. I didn't want to discuss this, but I'll do it. So what I mean is just that, maybe that's a good point because this is what we're going to do. What I mean is that these two equations here, they fix this two-point function to be this object. So this contactor here, the C, the constant depends on whether you want this current to be conserved or this current to be conserved. Because this anomaly, you can shuffle in this equation or this equation, doesn't matter. You just have to dualize the thing, and this thing will end up being here with the dual gauge field. So this C doesn't matter. But what I mean is that if you do a Galen-Newman decomposition of this thing, you get a massless spin. Like basically what I mean is that the rho 0 is a delta function of S, and you have a massless spin 0.
Good. Thank you.
You're welcome. Okay, so for the first part, I'll explain the general structure of these theories, and then I'll discuss two examples more precisely. The first one is going to be a slight variation of a superfluid, which is the simplest toy example of linearized gravity, and then I'll discuss linearized gravity as a second example of this general strategy. So, right, so as I told you here, this current K is what we call a magnetic current. And electric and magnetic don't mean much, they just mean that the magnetic current is conserved thanks to a Bianchi identity, and the electric current is conserved thanks to the equations of motion. If you dualize the theory, these two symmetries exchange. So like this is all I say by electric and magnetic. And if you want that, in this talk we're always going to claim that we want to preserve the magnetic symmetry, which is the one coming from a Bianchi identity, and the electric symmetries can get modified by interactions. And a way to do this is to engineer this. Okay, and I will always have two currents. I will always have J and K. J is the electric current, K is the magnetic current. And the reason why I need two currents, in the very low energy effective action, they're just the star of another. So in NM you have F and star F, and this is true. But once you start adding irrelevant corrections, J gets modified, but it's still conserved thanks to the new equations of motion, and K does not get modified. So this is why I want to separate them, despite the fact that in the really low energy effective action, these two currents are the same up to H star. And so to describe these things, I'll start with the regular higher form symmetries, and I want a current J, which is a P plus 1 form, because I'm talking about a P form symmetries, which we take to be closed. And this implies that there exists a magnetic current where the magnetic current, in this case, is a D minus P minus 1 form, which is just the star of the closed current. And this is enough to show that, so if you compute so this is just a divergence in form language. So this is the divergence of J. This object is going to be star D star squared. Sorry. I want to compute this object. And this is 0 because this thing is closed. So implying this condition is enough to get a conserved magnetic current. And you can try to trivialize this condition if you write this locally as the D of a P form field. And note that this introduces a gauge symmetry where you can shift this by an arbitrary P minus 1 form. And in general, if you have light electric charge matter, this will spoil this conservation. But if this matter is gapped, then the structure is there. And so if you compute dk, what you get is the Laplacian on A. So this is the gauge invariant version of a Laplacian, so it's not really d mu d mu phi, but this is the correct definition of the Laplacian, so that this thing is gauge invariant. And so you see that this is a wave equation for a massless field. So you have a massless p-form field in the game. And now if you want to write an effective field theory action that reproduces this physics, then the canonical thing to do is to get a build a Maxwell type action where you square this current and you contract this p plus 1 indices between the two currents. And so this theory here is a theory of a free p-form symmetry, free p-form field. Okay. So, as I told you before, in general, J and K are not the same current. It's just in the low energy effective action, they happen to be the star of each other. But this is not true as soon as you put interaction in the game. And so now that I've described this simple setup, I want to talk about biform symmetries. So we're going to do exactly the same. So we want to reproduce this discussion, which was for a regular p-form symmetry, for an object now, which we call a biform symmetry. So let's explain what I mean by that. Now we're going to consider a current, J, which has two sets of p plus 1 indices that lives in this GLD representation, which means that these p plus 1 indices are all completely antisymmetric. These p plus 1 indices are all completely antisymmetric. They're symmetric under the interchange of the two columns. And moreover, if you antisymmetrize a complete column with any box of the second column, this gets 0 for you. So to bring you back to some things that you know, the Riemann tensor is what I will call a window tableau. So it has two antisymmetric indices, two antisymmetric indices. It is symmetric under the interchange of both, and it solves the first Bianchi identity. So this is what I'm going to call a 2-2-by-4.
Sorry, one more question about the simple example. So here J is closed, but in the superfluid case it was also conserved. Really doesn't look obvious. The original one. Is it also conserved? K is conserved. You showed from closure of J. J should be electric.
J is conserved. Yeah, but J is conserved because of the equations of motions.
But you brought the DFT that you brought there also gives conservation for J. Okay.
Yes.
No. Yeah, why?
Well, because if you go back to the superfluid example, the current will just be d mu phi, right? And then this is d mu phi, d mu phi. The equations of motion are box phi, and d mu j mu.
Okay, but that seems to depend on what your fields are. Like if you're using that J is the derivative of something, and then you're writing the equation of motion varying phi. But I don't know, if I just took J to be the field and they vary, I just get J equals 0. I mean, what tells me what are the correct degrees of freedom today?
Well, you want to engineer J such that this is electric current, which means it is conserved on shell.
Okay, so it's not implied by this.
No, it's not implied by this. This implies the conservation of K.
Yeah.
This implies the conservation of K, not the conservation of J itself. J is going to be conserved on shell only, while K is conserved due to Bianchi identity, so it's just topologically true.
So this is a theory of a P-form field.
Yes, massless P-form.
Massless P.
Okay, so now we're going to look at currents.
Sorry.
Yes.
I think in a given dimension, you can't have arbitrary long line, right? For example, in 4 dimension, you can have a maximum of 2 boxes in the vertical line of Hilton. With a representation of this it's a B.
is saying in 4D I cannot build an arbitrary
Yeah, you
number.
can build arbitrary number, right?
You can build up to D, but you can change it using epsilon so you will have fewer.
Yeah, no, I think it's fine. Okay, so this is the structure that we want to play with, and luckily for us, this type of biforms have a whole exterior derivative, exterior calculus associated to them. And in particular, what we're going to do is we want to. So, in practice, you could dualize any of those columns, right? Because if you act with an epsilon on this column, because this thing is symmetric, it doesn't matter on which column you do that. But for our purposes, we want to not leave the space of things that have two equal length columns. And so the right thing to be doing is to double Hodge. So what I mean by a Hodge in front and a Hodge after is that you take a Hodge star on this column like in a regular form, and you take a Hodge star on this column like a regular form, and you end up again with a biform. Okay? And so as before, you can write the closeness condition of the current J. So this is really the analog of this one here. And what I mean by that is there is an unambiguous definition on how to act with this differential to create a P plus 2, P plus 1 biform. And this thing automatically makes the conservation of this object manifest, the same as before. But now the difference, so before we were using the Poincaré lemma, right, that tells you that d squared is 0 to write J as d of something. And in this case, the Poincaré lemma is slightly different, and it is that d cubed is 0. And the naive way to understand that is that if you add with 1D, you're going to add a box here. If you add with a second D, you're going to add a box here. If you add a third D, you're going to add a box here. And because you anti-symmetrize over the columns, this is going to anti-symmetrize two partial differentials, and this vanishes. And so the correct way here to trivialize this condition is to write the current J as d squared of a PP form. And note that this introduces also a gauge symmetry where you shift H by the D of a P minus 1. Okay. And if you build an EFT now with this current, the same way as I built an EFT here, this thing is guaranteed to be invariant under the symmetry that they care about. So let me do that. So the naive guess would be that to build an EFT with this current, you need to write a Maxwell type action. So you write this squared. But if you do that, you soon realize that you run into a problem because the equations of motion for such an action are d squared k equals 0, which implies box squared equals 0. So as a side note, this thing is conformal gravity, but this is not linearized gravity. So it has a fourth order equation of motion and not a second order equation of motion. And moreover, you have broken the symmetry because, well, I told you that, we were looking for objects, J and K are symmetric under the integer of a star. And here you have a d squared K and only dj. So you have broken the symmetry between J and K. And so this cannot be the right action that you're looking for. And the way to actually make an action that does what you want is to do something which has more the flavor of a Chern-Simons action than of a Maxwell type action. And the way to do this is to introduce the trace. So I want to introduce a trace.
Sorry, just to see if I
Yes.
So if P is 1, then H11 is like a metrical equation,
Yes.
and then
So-
this square is forming the Riemann or the
Yeah,
value?
exactly.
or
No,
the
it's forming
value-
the Riemann.
The Riemann tensor.
So right, the Riemann, so in this way of writing things, I was about to say something like that later on. Riemann is d squared h. So you know, it's an antisymmetric derivative of a symmetric two-index object. And so this current is really, this object will really be Riemann for a 1-1 form.
And then the action is the Riemann square instead of 3.
Yeah, and well, yeah. And on shell, Riemann square is the same as life square, and yeah. And so it leads to a fourth order equations of motion, which are not, the linear gravity has second order equations of motion. And so, yeah, to do that, we need to introduce another structure, which is the trace. So in particular, these objects have only one trace in them because of the symmetry of the object itself. So you can trace over any two boxes of these columns, doesn't matter. And if you trace a PQ form, you get a P minus 1, Q minus 1 form. And so the current equation, the correct equations that we want to look at are that this J current is closed, and that the trace of this object is and so in particular here you have a wave equation for H. And well, it does not take a lot of convincing after Joao's question to realize that this is the Einstein equation. The trace of the Riemann is 0. It's just the Einstein equation. For P equal 1, and for higher P's it's going to be something more involved. And also, this guarantees that this current is also solve these two equations. So these two equations imply these two equations. You don't need to work hard.
Can I ask, I want to ask a super dumb question, but to understand, because I got lost on the biforms, what's the difference between a 2 form and a 1-1 biform?
The 1-1 biform is symmetry.
Okay.
Right, because a 1-1 biform is this object, and a 2 form is this object. So one is symmetric and one is antisymmetric.
Can I also ask, is there a generalization of the RAM cohomology for this dq equals 0?
Yes.
Okay.
Yeah. Actually, that's another way in which you can arrive to linearized gravity. So that there is a cohomology structure where, I mean, you don't even have to talk about biforms. The only thing you have to do is you start with an object like that, and then you define a dr and a dl, where the dr acts here and the dl acts here, and then if you do that, d squared is 0. So, no, sorry, dl dr is not 0, but as soon as you eat with another dl or another dr, you get 0, and this, like, there's a cohomology, and you can follow, if you start from the window tableau, you can follow down and show that, you know, this is the only thing from which you can write the Riemann. Yeah. Actually, like, this is what we did at the beginning, but once you, actually you can show that, you know, if you start with this, you can show that this forces the Riemann to be what it is.
Actually, I guess you haven't defined for us what D actually does. Is it just a symmetric combination of this DL and DR that you mentioned?
Yeah, so, okay, so D, if I act with one D, I'll put it, like, I want to add boxes like that. So if I act with one D, I'm going to anti-symmetrize the partial derivative with all the first column.
On the left or on the right?
On the left first. And if I act with the second D, I'm going to anti-symmetrize this on the right. So if I was not talking about biforms, I would have to tell you this. I would have to define two things, DL and DR, which keep track of where I add a box. But because this biform has a symmetry structure where I can interchange all these things, this is actually, I don't need.
When you act with an odd number of these, we break this in the food. When you act with an odd number of these.
Sure. Sure, but if I act with the odd number of these here or here, it doesn't matter because I can swap those two columns completely. So like if I have an even number of these, it doesn't matter because it's a biform, and if I have an odd number of these, it doesn't matter either because this. If it's not a biform, so if you just if you start from object like that, then indeed I have to tell you whether I act here or I act here. But once I've told you that this thing has this symmetry structure and that it's like I can interchange under the two groups, then I don't need to do the distinction. And actually you can build E and M in this language, but now you have to take what we call the hot biforms. So these things are like, they are biforms where you have one plus more here to begin with, and then I have to tell you the other version you are. Fine.
Sorry, what do you mean by the trace equation? I mean, it's a Ricci scalar to be 0, it's a Ricci tensor to be 0.
No, this is going to be the Riemann tensor.
Yeah, but you have a trace on it.
Yeah, but if the Ricci tensor is 0, the Ricci scalar is 0. This is a trace of something that's 0. So it doesn't matter. But here I mean only a single trace.
Oh, okay.
It's a single trace. I mean, I can do that many times and remove all the traces, but here I'm taking only a single trace. And so I don't know where I was. I'll maybe keep that. So I'll show you that the Maxwell action does not work. And so the action that we're looking for is a bit more of the Chern-Simons type. And to be able, what I mean by Chern-Simons type is that the equations of motions are a partial flatness condition, and not this d squared that I just defined. And in particular, if d is greater than or equal than 2p plus 1, this partial flatness condition does not imply that the current equals 0. So trace G does not imply that J is 0. Or does not imply that J is 0. So you see that when P is 0, you have a funny superfluid which is not completely 0. And when P is 1, this is linearized gravity, and it's true that the fact that the trace of the Riemann is 0 does not imply that Riemann is 0. It implies that whatever is not vi is 0, but you keep the vi part of the Riemann tensor. So this is really the content of these equations. And to define the action that I'm looking for, I need to define another object, which is a PP biform, and is the Einstein tensor. So for 1, 1, this thing is really going to be the Einstein tensor. And in particular, it is conserved thanks to the fact that the current J is closed. And I think now I'm ready to write the action that I want to look at. So this action has this form. So it is H times J, where let me put a hat on this piece. I contract all the p's with all the p's and all the p tilde with all the p tilde. And this action is gauge invariant up to boundary terms, like Chern-Simons. And the equations of motion are...
You've not defined G, I think.
Yeah, I wanted to not define it, but if you want me to define it, I can define it. So dp is the sum k goes to 0 to p of some number so you take etas, which is the flat background metric, and you wedge that with all the traces of J, there is a combinatorial factor that comes from this wedge thing, and there is a unique object that makes this combination into a BP biform. And this is, if you look at that for 1, this is literally the Einstein tensor. Right, because you're going to have eta to the 0 times the trace of j, and eta 1 times 1 trace. And this factor is going to give you the -1/2 that you need for this to be the Einstein tensor.
Can k be bigger than 1? Then you will desymmetrize the column.
Yeah, no, it's just, you know, you take eta, wedge, trace. I mean, k cannot be bigger than p because then you cannot trace anymore, but it can be bigger than 1. And you sum all these terms. Okay, so, and this equation here, in the usual language, is really the statement that this is conserved. And in particular, the fact that GP is 0 implies that all the traces of K are 0. Because this is a flat metric, you can take it to be just eta mu, and so this implies, so yeah. The equations of motion being J equals 0 implies that trace J equals 0. And so this action reproduces this structure with the two current JK that we're looking for.
So you're varying age
Yes.
to obtain the equation of motion.
Yes. Well, it's the same as, so in linear gravity, you can write Field's Pauli action as h mu g mu by integrating by part a few times. And this looks like if you were to vary this with respect to h, you don't get g mu because g mu depends on h itself, but actually you do. Like if you integrate by parts enough times and you move terms around, that's exactly what you get. So this is the generalized statement of this fact. And in particular, these two currents are going to have an anomaly relating them. So let me not discuss the anomaly in the general setting, because I think going to a specific theory is going to be helpful. And let me talk about the first example, which is what we call the Galilean superfluid. And this thing is this general structure for p equals 0.
Sorry, so previously you explained that for higher form symmetry, it acts on objects by gravity.
Yes.
Is there a similar thing for biform?
Yes, but you need to somehow get rid of half of the guys.
How?
Yeah, I'm gonna say that later on. So I don't know if I say what. Basically, for example, if you want to compute a charge, okay, let me make an abort here. If you want to compute a charge, you can do that. But basically, what you need to do is contract this current with a killing tensor. So, you know, if you want this to be, you can look at what it implies for this quantity to be conserved. This gives you an equation on these tensors here. This equation, these tensors are called killing Yano tensors. And if psi solve this thing, this object is conserved, and you can integrate it over p minus 1 surface, and you get a conserved charge. Yeah, it's the same as when you contract T mu with a killing vector to construct it.
So for reality, what are these?
I'll tell you that later. That's not a spoiler surprise.
Okay. So for general P, can this be seen as equations of motion for some symmetric spin P field or to P field or not? Like Fronsdal equations? Or
No.
No.
No, because these objects are fully antisymmetric. You would have to. I mean, you can construct something. You can construct something along these lines for a Fronsdal field.
Okay.
You just need to change the structure a bit because these objects do not have higher spin fields in them.
Okay.
Okay, so let me. So what I want to do here, I want to start with this structure of currents, and then I'll tell you what the action is in this case that reproduces this structure. But let me be agnostic about that to begin with. And so I'll start with an object, which is a symmetric two-index object, which is a double derivative of phi. And this object is really just, well, it's the simplest biform for p equals 0. And in particular, this is invariant under the following symmetry, where you shift the free scalar by a constant shift plus a linear shift. And the free scalar has this symmetry. And this current here is the Noether current associated to this symmetry. And so, in this case, the current K is going to be stored J star, which is a nudge on this D and a nudge on this D. And this thing is automatically conserved. And so, as I told you before, now the equation are that the trace of this object is 0, this object is conserved, and you can write the equation for K in terms of J, and so you have a current that satisfies all these 4 conditions on shell and at separated points. So this one is true only on shell, this one is true of shell, and so on. And so you can obtain this thing from just a free scalar action, the d mu phi squared, but it's actually better. We want to use this general form of the action that we just advocated for. And in this case, this action is really simple. And this is the following action, which you should really see as a Palatini version of a superfluid. So I introduced an auxiliary field S, and if I look at the S equations of motion, this implies that S mu is d mu phi, and the phi equations of motions imply d mu S mu equals 0. So this is the Einstein tensor in this case. It is for p equals 0, this is a scalar. And it's clear that these two equations together implies box phi equals 0, as it should. And you can also check that if you integrate out S mu using the equations of motion, you just get back d mu phi squared.
I'm confused. If I use the first blackboard, H became phi, right? For p equals 0.
Yes. So H is a...
And G is just del squared phi, no?
So the equation was that G, p plus 1 is d squared H p.
Yeah, that was fine, but if I compute what you call the Einstein tensor, isn't it just box phi? If I use that formula?
Yeah, sorry. Well, but
it's probably equivalent, but if I use your formula, I will get a simpler action, like phi box phi, no? You introduce it.
yes, but this is the same action. This is phi box phi is the second order form of this first order action. If you integrate out S using this relation, you get phi squared phi. Okay? And so now I want to gauge the symmetries, and to gauge the symmetries, I will introduce a two-index diagonal gauge field, which is symmetric. And so let me call this action S0. And the action, so I need to add the coupling between phi and d mu nu. And then you have two terms which are on the contactors. And this is invariant under the symmetry where you shift where you shift a mu by the derivative of a vector. So the reason why you want to do this is because you want the subject has to be symmetric and you want the current to be conserved. And so it has to be the derivative of something such that when you integrate by parts, you get a conservation equation. And for an appropriate choice of C1 and C2, this action has this symmetry. And in particular, so if you vary the action with respect to the background gauge field, this gives you the current, and this current is this object plus term that depends on A mu. And so here there are two ways to do that. Either you come up with an action and you add contact terms, you brute force vary, you get an action that's gauge invariant, and then you vary the action with respect to the background gauge field and it spits out the current. Or, as you do in E and M, you know what the current is, and there's a unique tensor which has the correct symmetry to cancel the variation of this guy under this. So, and those two ways leads to the same thing. But in particular, now it is clear that if you compute the antisymmetric derivative of g nu, this term vanishes, but not the other one. And so you get something which is d nu, alpha beta, plus all the terms that you need for symmetry purposes. And so you see that these things are true, but this one picks up an anomaly. And there's no way to avoid that. Well, you can put it in another equation, but you will have an anomaly. And so now we want to, well, basically we want to inverse the logic and say, oh, we can define one of these funny Galilean superfluid as a symmetry, as a theory that has a two-form symmetric current, magnetic K current, and this anomaly. And as I told you for the regular superfluid, these four equations are enough to completely fix the two-point function between those two currents to be this plus contact terms. And if you do a Callahan-Lehman decomposition of these things, you get a massless scalar again. So here we have described the simplest case, and the second simplest case is the one of gravity. And in gravity, you have p equal 1. And in this case, you have two currents. One is this window current, and the other one is the bigger thing, where this is length t minus 2. And it is clear that this current, the trace of this current will be 0. This is going to be the Einstein equation, and this current is conserved, which is also true of the Riemann tensor in inverse gravity.
D minus 2?
Yes, sorry, D minus. Yes, D minus 2. Yes. And you have the same equation before the anomaly.
Sorry, the derivative there should be the covariant derivative rather than
This one?
yeah.
No.
No? So you're in a fast Fastest space?
Yeah.
Oh, I see.
Well, I'm in Euclidean space even. I'm in flat Euclidean space. And the same is true for K. And as for this superfluid, you will see that there is an anomaly. You're forced to have an anomaly, and now you can decide where you want to put it. But here. So the divergence of J is 0, and trace K is 0. And now dk is not 0. Dk is the third derivative of A, which is not 0. And so these 4 equations are enough to tell you that this is linearized gravity.
What is A here? What is the gauge field for what?
Yeah, I was about to describe that when I wrote the action. A is the gauge field for this object. So it is a window that couples to J in the action. And so it's really the same as when you have Maxwell, right? The magnetic Bianchi identity picks up the field strength of the electric symmetry. So it's really the same. J is the electric symmetry, and this guy is the field strength of this electric symmetry. And in particular, these 4 equations are enough to fix this 2-point function to be 1 over p squared times a massive tensor structure. But once this is true, then you can just show you can do Kahn-Lehmann decomposition, and you can show that the only state that appears in this spectral decomposition is a massless spin 2. And hence, this structure here protects the gaplessness of this massless spin 2.
So the massless mode is the only mode in this theory, or there's still massive modes?
Not without adding other terms to this action.
Because if you have a higher derivative terms, you may have a massive mode.
Yeah, but you have to check that these higher derivative terms do not spoil the biform symmetry.
Okay.
Not all of them are compatible with. In particular, if you want to preserve the biform symmetry, you cannot. So you can add interactions to this thing, and you'll get more terms. But the interaction that would make this into a fully nonlinear GR do not preserve the biform symmetry. So you cannot add them trivially. And so, so the action that you want to look at has this form. So here I have again written the action is in the first order formalism language. So I have introduced a free index object, which is a hook. So it's antisymmetric in the 2 first indices. And I have H and a hook. In particular, this object is really going to be the Einstein tensor once you work out the equations of motion. And this action has diffeomorphism invariant. And the hook equations of motion imply that this thing is an antisymmetric derivative of the metric, and the H equation of motion implies that the Einstein tensor built from this hook is 0. And so you see that this action is a bit like a mixture of Maxwell and Chern-Simons, because you have Riemann, which is fully gauge invariant, but the equations of motion are a flatness condition. But a flatness condition which does not set the whole Riemann to be 0, but just the traces of Riemann to be 0. And let me just conclude by describing the Iframe symmetries that this action has. There are 2 of them. One is the one I described at the beginning, where you start by shifting H mu nu by a constant symmetric to index object B. This thing is a symmetry of this action, but the problem is that if you compute the Noether current, this object is an antisymmetric derivative of h plus other terms, and this cannot be gauge invariant because we know that there is no single derivative object in linear gravity which is gauge invariant. So this object is not gauge invariant, but it provides well-defined charges because its divergence is the Einstein tensor. So it is conserved, and you can integrate it to get a charge, but it is not gauge invariant. So let's not talk about this thing, but this is one of the set of high form symmetries. And the other ones are the one where you shift h mu by the derivative of a hook free field. So this thing belongs to this representation. It is antisymmetric in the two first indices. And okay, you can work out how gamma has to transform, but in particular, if you introduce a background gauge field, this object will transform as this, where A is a traceless window field. And so, if you vary the action with respect to this A field, it will not come as a surprise that what you get is the Weil tensor. So if you do ds, dA.
So the action doesn't have an A field.
Oh yeah, sorry. Yeah. Okay, I agree. Okay, believe me, because well, I'm running out of time, but like you can do the same as what I did before. So you can add a coupling between h and nu and a double derivative of A and a bunch of dA squared terms, and there is a set of parameters that makes this action gauge invariant under this symmetry. Once you have this action, which is really long to write, and you vary this with respect to A, this spits out this minus a massive tensor, which we call C, and C here is schematically D squared A. And what I mean by that is that there is a unique tensor C that you can build, which has two derivative maximum A, has the symmetry of the Riemann tensor, is traceless, and has a transformation under these symmetries which compensate for the 1 of phi. And this tensor is unique. So you can also just say, oh, I know that my current is Weil. How do I make Weil invariant under this set of symmetries? And that spits out C for you. There is a unique answer that does that. And so, okay, this is J. And so J is traceless because A is traceless, is conserved, is dual traceless because this equation is a bit empty here because as I started with the biform, dual tracelessness is the first Bianchi identity, and the first Bianchi identity is automatically satisfied by these biform fields. But it is not dual conserved. So if you do d alpha, j mu, u rho, and you antisymmetrize over these three indices, this thing is minus d alpha c mu mu. Right. So the Weil tensor is dual conserved, but this new current is not dual conserved. So this is how you arrive to this these three equations with an action. And this is an action, like this action was written by Deser a long time ago. This is a first order formula. It's really just the Palatine formalism of linear gravity. But the advantage of going to first order formalism is that it decouples these two symmetries. Okay. So
I think you're out of time if you can conclude.
Yeah. So let me just conclude in words. So you can once you have this object, you can contract it with a killing tensor, conserve charges. We checked that these conserved charges are there and that you have a metric of linearized gravity which is charged under the symmetries, and it picks up 20 charges in 4D, which are known to exist and are the charges that were discussed previously in the literature. And so here we really wanted to advocate that, as in E&M, where Maxwell, I mean, the fact that you have F and star F, and the anomaly structure fixes the action to be F mu squared, you can do the same for this kind of biform symmetry structures, which are a bit more exotic, but you have a whole class of families now that you can just explore using this formalism. And in particular, we expect that you will have a massless mode in all of them. And so, as a future direction, well, there are many things that one can try to do with that. The obvious candidate is try to go to non-linearized gravity. And as I told you before, this is hard because the term that you need to add to make this action non-linear gravity do violate these biform symmetries. And well, we all know that a UV finite quantum gravity theory cannot have global symmetries, but somehow something should also protect the, at least in GR, nonlinear GR, some structure should protect this gaplessness of the graviton. And so it isn't clear that if you add all the new concept of symmetries, so like non-invertible symmetries, two-group, biform, higher form symmetries, you cannot come with the rigid structures that does that in nonlinear GR. And yeah, that was all.
Quick question. Like the construction is new type of biform symmetry, which has many charges, but to understand a bit better, what are the things that are charged under these symmetries? How should I think of these charged objects?
Yeah, so in 4D, what I'm going to say is really 4D. In 4D, the objects that are charged under them are Schwarzschild black hole. Linearized Schwarzschild black hole have a charge which is like if you integrate this thing. So okay, we took a metric which is a superposition of linearized Schwarzschild, linearized Kerr, linearized Taubenot, and linearized symmetrics, which are all known to solve linearized equations of motion. And if you integrate the star of this current with the killing tensor, you pick up the mass, the angular momentum. So yeah, you pick up the mass for Schwarzschild, the angular momentum for Schwarzschild, the nut charge for the nut solution, and the magnetic dual of the angular momentum, which is called acceleration for the symmetric. And so you can just check that you take linearized Schwarzschild, you take Weil of linearized Schwarzschild, you solve this killing equation, and you integrate that, and this charges are topological. So you can deform this thing, which is why maybe one way to make contact with this to something more known would be like because this thing are topological in practice, you can like deform them to infinity, and then this thing should map somehow to the ones Schrödinger and Friends are describing, because yeah, exactly. Like if you push them to infinity, the thing is, so in a specific number of dimensions, the killing equation is not sufficient. You have to require a Laplace equation on top of the killing equation, and this enhances the symmetry. And so for a 2D scalar, that's what gives you Kac-Moody. And Diego Hoffman and Nabil Iqbal have shown that for d equals 4, you get a Kac-Moody algebra for 4D E&M. And the number of dimensions work fine to pretend that this would happen in 4D linearized gravity. So we've not done that. In practice, you could do that, and you would get a symmetry enhancement. And this type of charges should be the ones Schrödinger. Well, this type of charges, when you push them to infinity, should be the ones Schrödinger and Friends are. are talking about.
And if you do this in ADS, you get just the conformality.
Presumably. Because this thing, so they pick up the Poincaré group, dilatation, and special conformal transformation. So yeah, we've not done that, but.
So can you explain? You said that you take this current and you contract with killing tensors.
Yes.
And then you integrate. Can you be a bit more concrete? Like in how many dimensions? Where do you integrate the current?
So it doesn't matter where I integrate this thing because they're topological.
Which dimension surface? What is it?
So it's going to be an integral over a two-sphere. So in 40 it's going to be an integral over a two-sphere. So okay, what you need to do is the following. So you take this object where this thing is a killing yellow tensor.
And this is the killing tensor in flat space.
Yes.
Because the background is still flat.
Correct. So yeah, so you ask what makes this conserved. This gives you an equation. This thing is conserved. This gives you an equation on this guy. You solve it, taking care of the symmetries. This gives you a killing yellow tensor, and the solution to this thing carries all the charges. And then if you wanna get the charges, then what you do is you integrate this object over a p minus 2 surface, which is a sphere in 40. And so we did this computation only in 4D, but you can do it in NED. And in particular, there is a charge without the star.
And you said there were 20 charges. This 20 is.
Yeah, in 40 there are 20 charges.
This is counting the killing tensor.
Exactly. So this thing has 4 different structure in the solution. It has a vector. It has 2 antisymmetric 2 tensor. And it has a 1 antisymmetric 3 tensors. And if you count the number of independent components of these 4 tensors, you get 20. And you can show that this thing really picks up all these charges. And this doesn't matter where. So this thing is topological. So you can just pick any 2 sphere that you like, and you can check that this does not depend on the.
But in your list from mass, angular, I mean, you didn't get to 20. Is this really? Are there objects with 20 independent charges?
Well, you would have to like superpose these 4 solutions, and like that would pick up all the charges together. So because like the metric that we looked at is a very peculiar metric. It is a solution of linearized gravity, but it is a superposition of Schwarzschild, Kerr, Dominant, and symmetry, as they call it. And once you integrate this thing, you pick up the 20 and 40.
Any other questions?
So this structure that we have with the biform symmetries and the hardform symmetries and the anomaly, do we know if it's protected under loop effect? Like if you consider loops in this linearized gravity, eventually you get counter terms. Is this structure solid enough?
I mean, the short answer is I don't know. We haven't checked. I claim that yes, but because you want to protect the magnetic current, so you can do whatever you want to the electric current, because as long as this is going to modify the equations of motion simultaneously, and then this thing is still going to be conserved. So the structure is pretty it's pretty good.
And also I have another question. So since you have formulated everything is formalism with the differentials and everything, is it possible to generalize it in like linearized gravity over a curve diagram? Like immediate?
Yeah.
It's doable.
Well, it's not as clean, right? Because like you lose the cohomology structure. I mean, you have to rework the cohomology structure to be sure that you still have this Poincaré lemma that holds, so that you can do that. But provided this holds, then yes. Because I mean, this construction is entirely based on exterior calculus. It's like it's just what it is. As long as the extra calculus works out, then you guarantee to have this to go along with the flow.
And if you do it in ADS and you get to the same 4D, you get maybe 10 instead of 20, so that it matches the conformal charges, then these should be preserved also by the interaction term, because quantum gravity in ADS is supposed to just preserve conformance.
Yeah, these charges, well, this is one of the reasons why we believe that, this story has to be modified for, nonlinear gravity, but some of these things have to, some remnant of the structure has to be there, because these charges should be there.
Right, but probably in ADS all of them, I don't know, the simplest thing is that you will be down to 10 in 4D, which are the conformal generators in 3D, and they would you just find terms that preserve them, or preserve all of these charges.
Yeah, they preserve the charges, but they don't. The problem is that the nonlinear interactions do not preserve the biform symmetry. So then, basically the problem is that in nonlinear gravity, I cannot write the Riemann as d squared of h. In particular, Riemann is not conserved anymore. The fact that Riemann is conserved, as a single divergence, is a linear gravity fact. It's not true in GR. So, yeah, you need to come up with improvements of the structure if you want to be able to add those terms that make it nonlinear.
But Einstein tensor is preserved. Right?
Yes.
So
But the Einstein tensor is conserved, but the current is not the Einstein tensor. It's the pi tensor. And the Riemann is the divergence of Riemann in GR is not zero. It is only in linear GR. And this is a consequence of the fact that you can write Riemann as d squared of h, which is not true in GR.
Okay, that's fine. Yeah.